Today, more than ever, the 3D graphics design industry is flourishing. Computer graphics design has become foundational for modern cinematography, gaming, architectural design, engineering consulting, and more. Creating accurate renders to represent the world being built is key to the development and value of the ideas being presented and experienced. Currently developing these renders is prohibitively expensive and time-consuming for independent artists or small studios to be able to present the world they envision for their audiences. Physically based rendering, or PBR, is an approach to computer graphics which simulates the physical properties of light and its interaction with materials to produce more accurate and realistic looking textures in the digital domain. The information to represent real-world materials is broken down into individual components, or texture maps, depicting roughness, metallicity, color, and more. To create PBR materials, artists need to scan real materials, spend time and resources capturing the texture maps and editing them or creating them from scratch. Automation can reduce the time required to translate information from the physical to the digital world and allows designers to further perfect artistic aspects instead. Introducing Graphos, the affordable, portable, and quick solution to your rendering needs. Graphos produces high-resolution textures anywhere you choose. Take it out of the studio, office, or home and into the world to acquire textures that are normally unavailable. Graphos has clear advantages versus competitors, such as low cost, portability, and independence from subscriptions. Graphos was designed utilizing simulations and implementing concepts from light transport theory to develop the features and advantages that serve as its functional foundation. The hemisphere design allows for a uniform distribution of light sources around the material being imaged. The distribution of light is imperative for the albedo map to be of high quality, as non-uniform light can lead to unwanted reflections and shadows. The light sources that allow for the highest light throughput at lowest power usage are LEDs, which are also light and inexpensive. The hemisphere is made with a matte black finish to avoid unwanted reflections on the material while scanning the normal map, which makes use of the optimal version of the photometric stereo technique. The hemisphere design includes an extension at the top, allowing the image sensor and lens assembly to fit within the device without making it larger. The assembly is made up of a moving camera that can capture images at different positions, stitching together 4 images of high resolution to make an even higher resolution image for each map. The advantage of such a design allows for a more cost-effective sensor and lens to be employed. To create a sensor that is capable of scanning material light interactions at multiple angles, cutting-edge software was used to integrate ray tracing simulations to create a material's bidirectional reflectance distribution function, or BRDF. This function is a mathematical tool that completely describes how light incoming from any direction reflects off of a surface. The information contains critical data that can be interpreted through PBR techniques to create photorealistic textures. The Brdf sensor uses a smart raster algorithm that minimizes the number of locations needed to determine all unique BRDFs of the texture. At each location, the Brdf sensor uses a set of RGB LEDs to represent a variety of optical source inputs and uses a curved array of linear photodetectors to maximize the number of data points recorded per scan. The scan records data from multiple angular configurations between the sensor and LED arrays. These datasets are aggregated and curve-fitted to estimate the material's unique BRDF. Information to create the specularity and roughness maps can be extracted from a material's BRDF. Additionally, a metallicity map can be created by combining data from the BRDF with the albedo map. This specific process was selected as it avoids any physical contact with the material's surface, which could jeopardize its physical integrity. The base was designed to perform 2 main functions. The first function is to charge Graphos, where it slots on the base for a perfect seal and is lined up to charge with no extra connectors. The second function is to provide a backlight behind the texture, which allows for the transparent properties of the material to be mapped. Uniform lighting conditions were created for the backlight to guarantee best possible conditions. While technical performance is largely the design focus, it is important to ensure that Graphos is never an inhibitor for exploration and acquisition of high-quality textures in their natural locations. Graphos is highly portable and easy to set up, detaching from the base to be placed anywhere. At the push of a button, the device scans a texture in as little as 5 minutes. The use of rechargeable batteries extends the opportunities and range of the device. The prototype brings together all the design elements to validate the expected outcomes of our analysis and simulations. The hemisphere has a mesh that supports an absorptive black material. The hemisphere LEDs enable the capture of the albedo and normal maps. The arrangement of the LEDs helps emphasize the shadowing effects. Graphos is in the final stages of development and ready to take the next step forward. From the darkness, Graphos provides the tools to illuminate and map your world.